blinding flash of light with an awesome amount of power. Incredibly, a typical star generates the equivalent energy of billions of hydrogen bombs every second of its existence.
The objects that populate the universe, the beasts and creatures that live out there, are rather remarkable, and they tell a wonderful story about how the universe has evolved.
Our human lives are so short compared to the evolution of a star. We can't see any evolution taking place. So it's really hard to believe at first that the stars really are changing, that they really are evolving.
Through an extraordinary chain of events, these beautiful night lights of the universe create the stellar power that shapes their lives.
Stars have to radiate energy from their surface. And that means they have to generate energy either by nuclear reactions, by gravitational contraction. In some way, they have to be generating energy inside.
The question then, though, is where does this energy come from? Because clearly stars are leaking energy all the time. When you look at the sun, that's obvious. So somewhere there's got to be an energy source that's replenishing the energy that's leaking out.
Surprisingly, the answer lies in the smallest particles, atomic nuclei.
There are lots of different nuclear reactions. First is the proton-proton chain, also known as the PP chain. In this process, 4 protons are mashed together into a helium atom, and a large amount of energy is liberated. So the first nuclear reaction has to be, you put 2 protons together, 1 hydrogen atom with the second one, and you make deuterium. And the second nuclear reaction, you take the deuterium and you put another proton on it and you make helium-3. The next reaction is 2 helium-3s slammed together, produce helium-4, and there's 2 extra protons left over.
So during the proton-proton chain, hydrogen nuclei successively collide to form helium. In the process, a tiny portion of mass is converted to energy in the form of gamma rays, positrons, neutrinos.
And what one finds is that the helium that results weighs slightly less than the reactant hydrogen. In other words, a little bit of the mass is no longer there. And what's happened is that the mass has been converted via a very famous equation, E equals mc squared, to pure energy. And so that's what powers the sun. The hydrogen is being converted into helium, and a little of the mass in that process is being converted to pure energy.
Okay, let's take a look at it now.
Each night, astronomers observe countless stars. Most fall within a well-defined range called the main sequence, a prolonged phase where the star's temperature and brightness change very little.
The theory of stellar structure tells us that a star is a ball of gas that is balanced between 2 forces. Gravity is trying to make the star collapse in on itself. But at the same time, the energy flowing out of the center of the star, that energy flowing outward is trying to make the star expand, trying to make it explode. And the star is balanced between those 2 forces.
The stability of main sequence stars is guaranteed by the fact that the nuclear reaction rates are so temperature sensitive. If one perturbs a layer, if you try to heat it up a little bit, then the nuclear reaction rates go way up. You might increase the temperature by 5%, but the energy generated will go up by a factor of 2, 3, 4, 5. All that energy escapes out from the star, and it pushes the layer back out. And so the layer then cools. And when it cools back down, the energy generation rates fall back to their original value, and stability is restored. It's like a thermostat that regulates the temperature and the structure of the star based on the properties of the nuclear energy generation rates.
we observe that massive stars, stars that contain a lot of matter, produce a lot of energy, and we say they're luminous. We observe that stars that have little mass have low luminosities. So there's a relationship between the mass of a star and its luminosity. That's an observational fact.
These relationships apply because it's the same sequence of physical laws that apply to all stars. There are both theoretical mass luminosity laws, which are based on the predictions of stellar models, and there are empirical ones based on our observation of stars in the sky.
Now we can understand the observed mass-luminosity relation because massive stars have a lot of mass, a lot of gravity, and that means they have a lot of weight pressing inward. And that means they need a lot of energy flowing outward to support that weight. So massive stars have to have a high energy flow, and when that energy gets to the surface, it makes them very luminous. Low-mass stars don't have very much mass, don't have very much gravity, don't have very much weight to support. They don't have very much weight to support. They don't need a high flow of energy out of the star, and that means they don't have to be very luminous.
If the star gets too massive, the radiation pouring out of the center of the star provides so much pressure pushing outward that it actually lifts the outer part of the star off and prevents the star from getting bigger than a certain limit.
Now, on the other end of things, that is at the low mass end of things, we are looking for objects called brown dwarfs, which would be so small in mass that they aren't really fully stars. They would never be able to burn hydrogen in their core and get onto the main sequence.
A brown dwarf can best be described in reference to regular stars. Our sun is a star with one solar mass whose luminosity from the surface is balanced by thermonuclear burning in its core. A brown dwarf is an object whose mass is insufficient to burn thermonuclear fuel at the center to compensate for its losses. So it will form from the interstellar medium as a regular star would, but it would not stabilize on the main sequence, the hydrogen burning main sequence, and it would cool off like a dying ember over the billions of years of its evolution.
People have thought there must be brown dwarfs around in large numbers for decades, and people had been looking for them, and no one had been finding them. One of the problems is that brown dwarfs may be substellar in mass, that is not big enough to generate energy in a sustained way.
Observing a brown dwarf will help to further clarify our ideas about how stars form and how they change over their lifetime.
How long does a star take to go through its life cycle? Stars are a little bit different from people. That most people live or can live, if you're healthy, about the same amount of time. But for stars, it's a little bit different because instead of taking in food from the outside, it's their own mass, it's hydrogen, which is keeping them alive.
The problem, however, is that the hydrogen will eventually run out and the gravity's just lying in wait. And so the question then becomes, what happens at that point when the hydrogen runs out?
The answer is that the core collapses. And as the core collapses, it's getting hotter and hotter. And eventually, some other reaction will turn on someplace in the star, either at the center or the hydrogen on the outside might start burning. Something's going to save it. But the core has to get hotter to turn on the next reaction, because anything involving other than hydrogen is going to need a hotter temperature to burn.
The end result is that the star is seeing much more energy flooding out from its central region than in the past, and that eventually has to work its way up to the surface. So the star itself increases in luminosity dramatically. The envelope of the star, most of the mass of the star, responds to that by saying, hey, there's something very, very hot all of a sudden in the central region that wasn't anywhere near this level before. And so the outer envelope of the star then responds to that by expanding. And as it expands, as the outer surface of this envelope, which is how far we can see into the star, cools. And so what we see from the outside is a much brighter object, a much brighter star, brightening, thousands of times over the current luminosity of the sun, and its outer surface temperature is decreasing, which drives it to higher luminosity and lower temperature on the HR diagram. And it drives it to a region which is known as the red giant area on the HR diagram. And the reason it's called red giant is kind of interesting in and of itself. First of all, we know that the temperature of the surface of that star has dropped. It's moved to a cooler area, a redder area of the HR diagram. And it must be a giant because we know that lower temperature objects per unit area put out much less energy. Yet what we're looking at is a very bright object. We now know in the interior of the star more energy is being produced.
Now the Sun as a red giant is going to expand into the inner part of the solar system. And so some planets, certainly Mercury and Venus, will do a slow death spiral into the middle of the Sun and get swallowed up. When the Sun becomes a red giant, the Earth is going to be uninhabitable. That the oceans will boil away, and instead of nice ocean waves that are going to lap against the seashore, you're just going to have very, very hot mud. Human beings don't survive very well at temperatures of around 1,000 degrees. So I think we're going to have to call it quits.
Now, this red giant will eventually reach a point where the core temperature, which has been steadily increasing, reaches something like 100 million K, 100 million kelvins. And at that point, the helium core now serves as fuel.
The helium that's now in the center of the star is going to start to fuse and is going to form carbon. It happens all at once, not just gradually from the center burning it out, but all of a sudden, bing. And then what happens is that the Sun is going to settle down, it's going to shrink a little bit, and eventually the helium's going to run out.
At this point, the star stops burning nuclear fuel in its core. It only burns fuel in shells around the core. And it becomes unstable. It's a very large star, bigger than the orbit of Venus, and in some cases the planet Earth around our Sun. And the outer envelope of the star gets blown off in a relatively mild eruption that forms what's called a planetary nebula, a very beautiful object in the sky.
And as this ejection takes place, someone outside looking at the system sees a shell of expanding gas. And so the end result is a ring-shaped appearance because the thin region that you're looking through looks transparent, while the outer layers, which you're looking through a longer column length, become opaque. So the appearance then is a ring structure with a central, very bright, exposed core.
Planetary nebulae, as well as mass loss in a more quiescent phase from stars, allows the stars to get rid of their outermost envelopes, leaving behind the carbon-oxygen core. And that then forms a very interesting, dense, compact object about the size of the Earth, which we call a white dwarf.
A white dwarf star is a tiny ball that is just about the size of the Earth. And if you were to take a cupful of white dwarf stuff, if this glass were filled with white dwarf stuff instead of water, I wouldn't be able to hold it here because it would weigh as much as 24 elephants. So white dwarfs are made of very, very dense matter.
The gradual fading and decline of a white dwarf is a very slow process. The planetary nebula remains visible for perhaps 10,000 years. The white dwarf will remain visible for a period longer than the present age of the universe. That is to say, no white dwarf has yet completely died.
Nuclear fusion does not occur inside a white dwarf. So it is able to radiate away only the energy that is stored in the nuclei that comprise the white dwarf. But no new energy can be released through thermonuclear fusion. So the white dwarf simply cools down and becomes less and less luminous, less and less powerful. And eventually, it is simply a rock-like substance, although it's very different from a normal rock that you find on Earth.
Even though many stars evolve from the main sequence through red giants to become white dwarfs, the timescales involved can be vastly different.
Paradoxically, the more massive stars are not the ones that live the longest. Yes, they do start with the largest amount of fuel, but they burn it up enormously fast. A massive star like the 3 stars in Orion's belt, for example, all have about 30 times as much mass as the Sun does. But they are burning hundreds of thousands of times brighter than the sun is. So even though they start out with more fuel, they're going to go through it really, really fast, and they're only going to live about 1 million years or so. Whereas you take the sun, and it's going to live about 10 billion years. Stars that are smaller than the sun are going through their fuel even more slowly. And so some of them are going to last tens or even hundreds of billions of years.
Low-mass stars live a long time, and high-mass stars burn up everything and die very quickly. And so you see every one solar mass star that there's ever been formed in the whole galaxy is still there today. But the high-mass stars, you only see the ones that were formed in the last few million years. So when you start counting stars, the number of low-mass stars is infinitely larger than the number of high-mass stars.
And so now what we've done is follow an evolutionary pathway that has tied together a wide variety of different beasts. A main sequence star like the sun, a red giant, a planetary nebula phase, and a white dwarf. They're all the same.